All right. Okay, so first up we have George Ellis from Cape Town. He's going to be speaking on the evolving block universe. Did you need this? Are you going to be wondering?
I'll use this one. So, Hugh, thank you for making this thing happen. Very glad that you have come here. So, I'm, of course, a physicist. I will probably make some philosophical faux pas. So my philosophical backup is Tim Maudlin's book, The Metaphysics Within Physics. He's my witness for my defense when we come to the philosophy side. On the more general side, this Scientific American special issue, A Matter of Time, it's a great summary of all of it's for the popular audience, but nevertheless it's an overview of the arguments which we're discussing at this meeting, and it's a really nice place where it's all gathered together. So I'm going to put some controversial views, and I'm sure that a lot of you are going to disagree with me at various places, but I actually agree with Carlo in a very large part of what you're doing. It's the last part that we're going to disagree. So, the standard physics picture, time is an illusion, the block universe, we've heard something about that. I'll say a little bit more about that. I'm going to just briefly talk about that, then about taking time seriously. Time passes as regards the contents of space-time and the space-time itself, which leads to what I call the emergent block universe. And there are a series of objections which I will then try to counter. And then, if I have time, I will talk about taking quantum theories seriously, about talking of the collapse of the wave function as a transition event and issues arising from delayed choice, which lead to a further refinement, which I call the crystallizing block universe. So, time is an illusion. The nature of space-time in both special and general relativity has led some to a view that the passage of time is an illusion. Given data at an arbitrary time, it's claimed that everything occurring at any later or earlier time can be uniquely determined from that data. Time-reversible Hamiltonian dynamics provides the basis for physics in general and gravitation in particular. One can perfectly equally predict to the future and the past from the present-day data because of your Hamiltonian evolution. Consequently, nothing can be special about any particular moment. There's no special now which can be called the present. The past, present, and future are equal to each other, for there's no surface which can be uniquely called the present. And Julian Barbour, of course, is a particular example. In the end of time, I argue that apparent passage of time is an illusion. If we could stand outside the universe and see it as it is, it would appear to be static. Now, such a view can be formalized in the idea of the block universe. Space and time are represented as merged into an unchanging space-time entity with no particular space sections identified as the present and no evolution of space-time taking place. The universe just is a fixed space-time block representing all events that have happened and that will happen. This representation implicitly embodies the idea that time is an illusion. Time does not roll on in this picture. And so there's the block universe, space-time, time going up, space sideways. Both the past and the future already exist and are uniquely determined. Nothing unexpected can happen, so the present has no significance. And in fact, in almost all space-time diagrams, this present is not represented in those diagrams. Now, the problem with this view is that it's in profound contradiction with our experiences in everyday life, and in particular with the way science is carried out. Scientific theories are developed and then tested by an ongoing process that rolls out in time. Initially, the theory does not exist. It's developed, tested, refined, finally perhaps accepted. As in other cases, events take place. By contrast to this view, therefore, one can suggest that the true nature of space-time is best represented as an emergent block universe, or EBU, a space-time which grows and incorporates ever more events, concretizing as times evolve along each world line. Unlike the standard block universe, it adequately represents the differences between the past, present, and future, and depicts the change from the potentialities of the future to the determinate nature of the past. So things actually change in time. Now, of course, there's a tension we've already encountered between the macro and the micro level. Reversible laws at the micro level of Hamiltonian dynamics and irreversible at the macro level, where we have the second law of thermodynamics, which is the fundamental feature of the macro world of physics and chemistry and biology. And so we have, for example, the example Roger Penrose talks about, a breaking of a glass. If you take a film of a glass breaking, it falls to the floor. If you play that film backwards, people will say you're saying that you're playing it backwards. They will be able to easily identify the fact that this is not a motion which occurs in the real universe. And the processes of life are, of course, very importantly, time irreversible. We start off We're born, we live, and eventually we come to an end. That process has got this inevitability about it, which is the progress of time. In the real world, the past and future are not predictable from the present and are not Hamiltonian, which I will illustrate. So the solar system undergoes time-reversible Hamiltonian development, allowing exquisite predictions. But this is the exception rather than the rule. This allows very accurate predictions to the future and the past in the specific, almost frictionless case, but there are almost no things in the real universe that are in fact frictionless. And this is for a limited time, and it's highly exceptional. In the real universe, irreversible events happen. And Arthur Stanley Eddington, in a quote which I love, explained this very clearly. The second law of thermodynamics is entropy, randomness always increases. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observations, well, those experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There's nothing for it but to collapse in deepest humiliation. So taking time seriously in evolving block space-time. Consider a massive object with two computer-controlled rocket engines that move it to the left-right. So you've got a massive thing. There's an engine pointing that way and an engine pointing that way. There's a computer which decides which one will fire when. Let the computer determine the outcome on the basis of measurement of decay products of excited atoms. So you've got a radioactive source and a detector, and that source sends signals which are then fed into the computer to determine which engine will fire when. The outcome is then unpredictable in principle. I'm adopting the standard interpretation of quantum mechanics. And if the object is massive enough, it curves space-time. The future space-time structure is not determinable or predictable from current data. And it's been pointed out to me that actually this is what was the core of the Bohr-Einstein debate a long time ago. So here's the picture, the change from uncertainty to certainty. The present is where the indefinite future changes to the determined past. So on the left here, things are determined up to there, and then those are possible paths, and it's not yet determined which of those paths will be taken. Over here, time has moved on. These are paths which were not taken. The path which was taken is up to there, and those are now the paths which may be taken in the future. And so you've got your possibilities at each time. As time moves on, which possibility is taken and which is not taken keeps moving on. So this is the change from uncertainty to certainty. The present is where the indefinite future changes to the determined past. And okay. And because I have set you up a structure where what happens is determined on the basis of radioactive decay, what happens in the future is not determined by the earlier data. You only find out what the space-time structure is going to be as it happens. There is no way to predict in advance what the space-time structure will be. You have to watch what happens in that and find out what the outcome was, because that's the way I have set up this system. So the evolving block universe grows with time. The past has been determined and is fixed. The future is uncertain and still has to be fixed. Because of quantum uncertainty, it's not true that the future is determined at the present. The present is where the change takes place. It's crucially different from the past and the future, and indeed it separates them. It's the future boundary of the space-time. The space-time exists in the past and does not yet exist in the future. The future does not exist in the same sense as the past or the present. That's because you can be influenced by the past. You make your decision at the present, and the future can't influence you because it isn't even determined at the present moment. The determined region grows with time. Space-time itself is growing. So here's the picture. It grows with time as time goes on. Now, the paradox. This model of space-time is obviously far more in accord with our daily experience than the standard block universe picture. Indeed, every data, including the apparent passage of time involved in carrying out every single physics experiment, would seem to decisively choose the evolving block universe over the block universe. The evidence seems abundantly clear. Why then do some physicists prefer the latter? If scientific method is to abandon a theory when the evidence against it, why do some hold to the block universe picture? The counter viewpoint is put succinctly by Sean Carroll in a blog which resulted from the FQXI meeting which some of you were at. The past and future are equally real. This isn't completely accepted, but it should be. Intuitively, we think that the now is real while the past is fixed and in the books and the future hasn't yet occurred. But physics teaches us something remarkable. Every event in the past and future is implicit in the current moment. This is hard to see in our everyday lives since we're nowhere close to knowing everything about the universe at any moment, nor will we ever be. But the equations don't lie. I'm emphasizing that sentence. As Einstein put it, it appears therefore more natural to think of physical reality as a four-dimensional existence instead of, as hitherto, the evolution of a three-dimensional existence. So that's the counter-argument. But the question is which equations and when are they applicable? It's all very well having mathematical models, but you have to know when is a mathematical model applicable and when is it not applicable. When true complexity is taken into account, the unitary equations leading to the view that time is an illusion are generically not applicable, except to isolated micro-components of the whole. The viewpoint expressed by Carroll supposes a determinism of the future that's not realized in practice. Inter alia, he's denying the existence of quantum uncertainty in the universe we experience. But physics experiments show that uncertainty to be a well-established aspect of the universe as we experience it, and it can have macroscopic consequences in the real world. And in fact, this is demonstrated by the historic process of structural formation resulting from quantum fluctuations during the inflationary era. So here's the standard picture of the history of the universe, with the start of the universe over at the left at some quantum state, inflation, the afterglow of light after 300,000 years, the dark ages, and so on, and the present on the right. Now the key point about this, if you believe the standard picture of cosmology today, quantum fluctuations led to galaxies and large-scale structures. That's the whole inflationary picture. Quantum fluctuations in the very early universe were the seeds by which, on the last scattering surface, there were higher and lower density pockets, which then led to the formation of large-scale structures and galaxies and the Earth. Now, if you believe the standard picture, if you knew everything about the universe at the start of inflation, it's not possible for you to predict that this room will exist or that I will exist, that you will exist, because even the existence of our galaxy is not implied by the initial data at the start of inflation. Quantum uncertainty came in and created those fluctuations. Now, I hasten to add there's a huge hiatus in the theory here. There is not at the moment a current viable description of how those quantum fluctuations became classical, but let's assume someday someone will sort that one out. The point is that if you knew everything at the beginning of inflation, you had a total description of everything in the universe, you would not be able to predict that we exist in this room because of the quantum uncertainty which has led to those fluctuations which led to galaxies existing today. Those inhomogeneities were not determined until the relevant quantum fluctuations had occurred and then became crystallized in classical fluctuations. And they were unpredictable even in principle. So you can't say quantum fluctuations don't matter. They're crucial to the history of cosmology. Now, what about the problems with the view? The prime issue arising is that the space-time view of special relativity denies the existence of any preferred time slices. We've already heard about this. Whereas the claimed existence of the present in the evolving block universe is certainly a preferred time surface. At each instant, it's the future boundary of the four-dimensional space-time. So I'm going to look at that first. An array of further arguments for the claimed time as an illusion has been made by philosophers and physicists. I will turn to them next. I then consider the way the block universe relates to theories of the mind, which is a key problem for that view, and I then point out how it relates to the arrow of time issue and solves the chronology protection issue. If there's time, I will consider how it may be altered when one takes quantum issues into account. And I'm just recommending here the Special Scientific American issue. It's a convenient summary of all of these arguments against the picture that I've been giving. Okay, the primary problem is the claimed unique status of the present in the evolving block universe, the surface where the indeterminate futures change to the definite past at any instant. It's a fundamental feature of special relativity that simultaneity is not uniquely defined. It depends on the state of motion of the observer, and we've already heard about this. For different observers at an event P, different motions will designate different events Q on a distant world line as simultaneous with P. Hence, the block universe model is natural. It's the only way a space-time model can incorporate this lack of well-defined surface of instantaneity. Hence, time is an illusion. And so the point is that that surface of instantaneity is equally good with that one. You can't have any preferred one, and so there aren't any good way to define surfaces of instantaneity. Now, the resolution picks up where I agree completely with what Carlo was saying. Physically, things happen along time-like world lines rather than on space-like surfaces. And so my proposal for the time of determination is as follows. You start at the beginning of time, you measure proper time along fundamental world lines, I'll talk about those in the next slide, and thereby determine the transition surfaces of the present as time evolves along preferred fundamental world lines. So you start at the beginning of the universe, you measure proper time from the start of the universe to today, and that defines a surface which is a preferred surface in space-time. This is not globally coordinated by some non-local mechanism, rather it happens locally everywhere. So the local happenings add up to a global happening, but the global happening is secondary. What is primary is the local happenings where time is determined. So change happens on preferred surfaces of change that is secondary to time, like world lines. And these surfaces need not be simultaneous in the usual sense. In fact, simultaneity is usually defined, determined by radar, is irrelevant to physical causation. I'm repeating what we heard earlier. So physically, things happen along time-like world lines rather than on space-like surfaces. I think of this: on the left is the Earth, on the right is Mars. The people at NASA are controlling this thing moving on Mars. Now, what matters is the event when you send the signal, the event when the signal is received, and the event when you receive a signal back. That's what matters for controlling that thing on Mars from the surface of the Earth. What matters physically is E1, the emission, E2, the interaction, and E3, the reception. What you think of as simultaneous is absolutely irrelevant. It has nothing to do with physical causation. It's purely a psychological thing, what you think is simultaneous, so it does not matter. And so all of that debate about simultaneity, all that simple stuff in special relativity, in the end, it's about psychology, not about physics. What really matters, and Carlo has already said this, is proper time measured along timelines, determined by the metric tensor by the basic formula which he's already given you. That's the key thing whereby which time is measured and whereby which time happens. The natural surfaces of constant time are given by this integral since the start of the universe. So what I propose is the present, the ever-changing surface S tau, separating the future and the past. At the time tau is the surface tau is constant given by this integral along a family of fundamental world lines starting at the beginning of space-time, which is the boundary to space-time. And in all our present understanding of the universe, that boundary was spacelike. Now, you can have some models where there wasn't a beginning to the universe, then you have to assume there was such a surface and keep taking it up. But I'm going to take the assumption there was a start to the universe. Now, is this well defined given that there are no preferred world lines in the flat space-time of special relativity? Well, the second fundamental feature is that general relativity describes the structure of space-time, not special relativity. The special relativity argument's irrelevant because that isn't the way the universe is. Gravity governs space-time curvature. We've already heard that. And now the interesting point is the following. There's no perfect vacuum anywhere in the real universe. So people, general relativists, love to make vacuum solutions of the field equations, but actually there isn't a vacuum anywhere in the universe because cosmic blackbody background radiation permeates the solar system and all of interstellar and intergalactic space. So space-time is nowhere flat and is nowhere of constant curvature if you take a real model of the real universe. Therefore, there are preferred time-like lines everywhere in any realistic space-time model. The special relativity argument simply does not apply. A uniquely geometrically determined choice for the fundamental world lines is the set of time-like eigenlines of the Ricci tensor on suitable averaging scale. Now, the averaging scale is a deep issue which I'm not going to talk about, but that's where difficult problems arise, but I'm not going to talk about that. These time-like eigenlines will exist and be unique for all realistic matter once you've chosen your averaging scale because of the energy conditions all realistic matter obeys. So the velocities satisfy the equation that they're timelike eigenvectors of the stress tensor, the left-hand part of that equation, which is exactly the same as the timelike eigenvectors of the Ricci tensor because of the Einstein equation. So they are physically uniquely defined and geometrically uniquely defined. And so the equivalence follows from the Einstein field equation. So therefore what I propose is the fundamental world lines along which you take that proper integral is these world lines, the timelike eigenvectors of the Ricci tensor, which will be well defined everywhere in the real physical universe. Now these give the usual surfaces of constant time in the standard Friedmann-Lemaitre Robertson-Walker models of cosmology. If you apply this procedure to your standard cosmologies, it'll give you the answer you want, the standard surfaces of constant time. And
are you taking short questions or not? Are you taking questions at all?
if they're very short.
Well, why do you need to average at all? Why not just say at every point take the timelike eigenvector?
Because there's always an averaging in any description you have of any space-time. If you've got a density of matter, you have to have a volume in which you're averaging that density of matter. So to measure a volume, you have to have a volume in which you measure velocity.
Sorry.
There's always a hidden averaging scale in every description in physics. So here's a picture, the evolving block universe. The present is where the future changes to the past. It takes place along preferred time-like world lines, the average motion of matter in the universe. And I must emphasize that this definition, this is the average motion of matter, of all the matter and energy at each space-time point in the universe. Now what about simultaneity? In general, these surfaces are not related to simultaneity as determined by radar. Indeed, that's even so in a Robertson-Walker spacetime, as Carlo pointed out. In a Robertson-Walker spacetime, the surfaces of homogeneity are generically not simultaneous according to the radar definition. Furthermore, with my definition, the flow lines are not necessarily orthogonal to the surfaces of constant time in a general universe model with fluctuations. More than that, the surfaces determined in this way may not even be necessarily space-like. They may become time-like surfaces in a really inhomogeneous universe. But as I've said, these surfaces are secondary to the time-like world lines that generate them. No physical phenomena are directly determined by simultaneity. What matters is what happens on time-like world lines and not what happens on space-like surfaces. So that's my basic proposal. Now let's look at the further arguments, and there's 1, 2, 3, 4, 5 of them that I'm going to go through. Yeah.
The lines meet, can the world line meet?
If they meet, because they're time-like eigenvectors of the Ricci tensor, the density diverges, there's a singularity in space-time comes to
So they only can meet on similarities.
But they're time-like eigenvectors. They can't meet unless there's a singularity. Okay, I'm going to talk about rates of change, about time parameter invariance, about general covariance and local Lorentz invariance, the Wheeler de Witt equation, categorization problem, and not necessary to describe events. There's a detailed response in this paper which I put on the archive. Okay, a key question is how fast does time pass? And Davies and Carr and others suggest there's no sensible answer to this question, that it doesn't make sense to ask how fast does time pass. Well, I claim the answer is given by the metric tensor. We've already seen the formula. It determines proper time along any world line. The whole function of that equation is to tell you how fast time is passing. That's what that equation is for. This is the time measured along that world line by any perfect clock. Time changes at the rate of 1 second per second, and Tim Morden agrees with me on this. Or, if you like, it changes at the rate of 3,600 seconds per hour, but that time changes as you would expect. This metric is what fixes physical time, including gravitational time dilation. Gravitational time dilation will follow from this because the gravitational potential affects relative rates. Now, real-world clocks, oscillators that obey the simple harmonic equation, are approximations to the ideal clocks represented here, and it's the relation between these real-world clocks, oscillators, and other physical events that measures the passage of time. So, if the metric determines proper time, what determines the metric? Okay, well, the Einstein field equations, of course. Following Arnowitt, and Misner, the first fundamental of form is represented in the form which all of the physicists will know. For the non-physicists, I haven't got time to explain this. But there's a lapse function, which is an arbitrary choice, and a shift vector, which is an arbitrary choice. And they represent how time changes between surfaces and how the coordinate flow lines and the matter flow lines differ from each other. the metric tensor Gij is the metric of the three spaces T is constant. The second fundamental form is the time derivative of the metric tensor, and it's showing how the normals diverge or converge. The matter flows have the tangent vector u, which is different from n, and either you know the ADM formalism or you don't, and if you know it, I haven't got time, I'm afraid, to explain it in detail for those who aren't, except just to give you this picture. What you've got there is an initial surface and a later surface. There's a lapse function, which is how the coordinate time changes from one surface to the next, and a shift vector. The matter flow is not moving along the normal necessary. The shift vector tells you how you must move sideways to follow the matter from surface to surface. And in general, you can choose you can choose the lapse and the shift as you like. Those are coordinate choices which you can choose arbitrarily. So I've called it matter flow lines, but actually those are the coordinate flow lines. I'm going to choose them as the matter flow lines, but in general those are coordinate flow lines having nothing to do with the matter, but I'm going to choose them as the matter flow lines. Now, the field equations are given in a very well-known way. You have a constraint equation C1 determined by the energy density, and a constraint equation C2 given by the momentum flux. So you've got two constraint equations. This is standard general relativity. And then you've got the time derivative equation T1, which is a time derivative of the metric. And the time derivative of the metric, the key point here, the time derivative of the metric has got a source term pi. Where does pi come from? It comes from this equation. And this equation has a source term, the matter tensor. And so the way it works is that this is determined by that, this is determined by all of this stuff, but particularly by that. What is that determined by? It's determined by the matter equations of state and the matter conservation equations. So given the matter equations, which tell you how Tij is evolving and how rho is evolving and T mu naught is evolving, this is a complete and consistent set of equations, which is used in all numerical relativity, for example. And of course, you have to satisfy the conservation equations for the matter, which are in fact the equations of motion for the matter as a whole. So the point about this, that formalism, its power is it can be worked out for any choice of the lapse and shift. But what I'm going to say, we can adapt that formalism to the proposal I'm making. And so you choose a unique gauge by specializing the time surface and flow lines to those I've already defined. So you choose the flow lines to be Ricci eigenlines. That means you set T mu naught as 0, and that turns out to be an algebraic equation for the shift vector. And so you don't have to solve any differential equations. You algebraically solve for n. From that equation, the T mu naught is going to be 0. That's the prescription I gave you. And then you will know the shift vector at a point-by-point basis, and you will have solved the constraint equation C1. You determine the lapse function by the condition that the time parameter t measures proper time along the fundamental flow lines, and you just work it out that n squared must be 1 plus ni, that gives you n2. And we have then chosen the coordinates, the ADM coordinates, precisely as I said in my prescription of how we were going to choose those fundamental world lines. These conditions uniquely determine the lapse and the shift. They uniquely determine it because the matter density is non-zero. I must emphasize that. In the vacuum equations, these do not determine it uniquely. I'm relying on the fact that the matter density is non-zero to get a uniqueness out of this. So then, given the equations of state and dynamical equations for the matter, the time equations T1, T2 determine the time evolution of the metric in terms of proper time along the fundamental flow lines, because we have chosen a coordinate where we're measuring proper time along those flow lines. The development of space-time with time takes place just as in the case for every other physical field, with the relevant time parameter being proper time along the fundamental flow lines, because I've chosen time to be proper time. There's no problem with the existence or the rate of flow of time as regards the metric tensor and the way that it evolves. Time flows at the rate of 1 second per second as determined by the metric tensor locally at each event. The space-time develops accordingly via T1 and T2, and there's absolutely no problem about setting the whole thing up in accordance with the prescription that I've given. Now, do these equations mean the space-time development is uniquely determined to the future and the past from the initial data? Well, that depends on the equations of state for the matter content. And I must just remind you here, in these time equations, so whether it's determinate or not depends on what happens there. That's where determinism comes from, if there is determinism. What you can do is you can determine the isotropic pressure to be the trace of the 3-stress tensor and the anisotropic tensor pi to be the full tensor minus its trace. And then your equation of state can be that the anisotropic pressure is a function f of proper time tau times a constant matrix. And everything depends then on what f of tau does. F of tau represents local dynamics, and if that f of tau involves random processes, then the space-time will develop from the initial data in a way which is not predicted by the initial data, because it's been determined by the random processes involving an f. And I've already given you 2 examples of how that happens in the universe. This is what happened basically when the inflationary perturbations generated galaxies, or the precursors of galaxies. There was a function f of tau there which was not predictable, and so therefore this is where the non-predictability of the equations come from. We've got perfectly good equations. They are only predictable if the equations of state of the matter are predictable, and if they're not, then the space-time outcome is not predictable. So equations T1 and T2 determine the time evolution but do not guarantee predictability. Whether it's predictable or not depends on the dynamics that you have chosen. If quantum unpredictability gets amplified to macro scales, the space-time evolution is intrinsically undetermined till it happens, as during the generation of seed inhomogeneities in the inflationary era in the very early universe.
Good question. If you go back to the last slide, is this just for illustration that you're assuming that pi ij is just a simple multiple of pi ij of 0?
But just as a simple
It's just an illustration, but you don't really want to build that into the theory of matter.
No, I'm just demonstrating to you that these equations do not guarantee predictability.
Right, but these equations are just a very special case.
Yeah, that's a very special case. But at a certain level, this models what's happening in that inflationary picture, actually.
But for generic matter, you wouldn't expect pi ij to be a simple multiple of pi ij.
No, I'm just giving you...
Yes, okay, I just wanted to double check.
Yeah. Incidentally, for those of you who know the general relativity literature, Bondi wrote about this a long time ago, what he called Tweedledum and Tweedledee. Do any of you remember all of that? Okay, well, if you want to look up Tweedledum and Tweedledee, Herman Bondi, and you'll find an interesting discussion. Okay, time parameter invariance. What about the time parameter invariance of general relativity is made manifest in the ADM formalism? Okay, well, the gravitational side of ADM equations may be time parameter invariant, but the matter side is not. In particular, when the Lagrangian is a kinetic energy minus a potential energy, rescaling time changes the kinetic energy while leaving the potential energy unchanged, and it'll give you different orbits. In fact, if you change t to t primed as ft, it leaves the Lagrangian invariant if and only if you have an affine transformation of the time. Hence, any solution with matter present, that is, all realistic solutions, will not be time parameter invariant. So it's all very well having the gravitational side time parameter invariant, but the matter side isn't. This is part of the ongoing tension between the geometric and matter side of the Einstein field equations, which bothered Einstein all the time. Local physics does indeed have a preferred time parameter. For instance, for a simple harmonic oscillator using standard time t, you get q tau Acos omega t. These cycles measure physical time like a metronome. That's why you use simple harmonic oscillators as clocks. And so there is a preferred time parameter for local physics. That's what Newtonian equations are about. There's a time parameter there, which is a preferred time. And this time applies equally to all local physics. Each involves a time t. Newton's laws of motion, Maxwell's equations, Schrödinger equation, Dirac equation, the diffusion equation, they've all got a time parameter t. Now, the deep thing is that it's the same time parameter t in all of those equations. We would be in serious trouble in physics if you had different time parameters in these different equations. And one of the deep things of physics is it's the same time parameter in all of them. Given that there is a preferred time parameter which you can find from any of these equations, it's perverse to use any other time parameter except for the standard time parameter, which is unique up to affine transformations, which is just a choice of coordinates for the time. And what is this time parameter? It's just proper time tau measured along the relevant worldlines, which provides a preferred time parameter in general relativity theory to find up to affine transformations. And that proper time tau is under the standard interpretation of GR, what links into all of these local times, it links in the space-time structure through the metric into all of these local physical events. What about general covariance and local Lorentz invariance? Well, these are symmetries of the general theory, not of its solutions. Interesting solutions break the symmetries of the theory. This is not surprising, as we know that broken symmetries are the key to all interesting physics. Specific solutions of the theory have less symmetry than the theory itself. The symmetry breaking is a key feature of all realistic solutions of the field equations and particular cosmology. Cosmology does have preferred time sections, and it does have preferred proper time along those world lines. Now, this is where I'm going to get into trouble, the Wheeler de Witt equation in the mind. Julian Barbour, in The End of Time, says there is no time, the entire universe and everything in it is static and unchanging. Why? Because of the Wheeler de Witt equation, d psi by dt is h psi, where psi is the wave function of the universe. And the key point is for general relativity has a very, very special Hamiltonian, which acting on psi gives you 0, so d psi by dt is 0. The wave function is independent of time. And so therefore time is an illusion. I'm summarizing Julian Barbour's book in a very brief space. But, and I've asked Julian about this, if time is an illusion, how do we believe and experience time as changing? Now, Julian's claim in his book, there exist records of events that our brains read sequentially and so create a false illusion of the passage of time. I'm quoting from his book. Thus, brain processes are responsible for the illusion of change. Now, the present day view of neuroscience is that mental states phi are functions of brain states which are based in the underlying neuronal states, BI, determined by genetics and interactions in the brain, taking place in the overall environment. I'm more or less quoting Francis Crick. So your mental states are a function of your overall brain state, which is a function of your microscopic brain states and may have some input from the environment. If time doesn't flow in macrophysics in an unchanging environment, then B can't change because your Wheeler de Witt equation has said it can't change. The environment can't change because the Wheeler de Witt equation has said that can't change. And so your brain states can't change. And mental states cannot evolve. Now, Tim Maudlin gives the same argument in different words. Daily life proves this theory is wrong. Julian Barbour's whole argument depends on rejecting all of present-day neuroscience. It depends on having a dualism in which mind processes are not caused by the brain. Well, I don't think we can go with that nowadays. If you have a non-passage variant which results in effective flow of time in our brains, then time is not an illusion at the macro level. So, Arnowitt and Dazer and Misner, in fact, write of the Hamiltonian formalism as follows. Since the relation between Qm plus 1 and tau is undetermined, we are free to specify it explicitly, i.e. impose a coordinate condition. If in particular this relation is chosen to be Qm plus 1 as tau, a condition which also determines n, this is exactly the choice that I made, the action 2.4 then reduces to 2.5 with the notational change Qm plus 1 goes to tau. The non-vanishing Hamiltonian arises as a result of this process. In other words, Arnowitt and Dazer and Misner are saying if you choose the special coordinate system which I've said, then the Hamiltonian does not vanish. And in that case, the Wheeler de Witt equation will not give you d psi by dt is 0. The Wheeler de Witt equation will not apply for Hamiltonian dynamics in that frame. And incidentally, unimodular gravity also gives you a similar result. More fundamentally, from my viewpoint, quantum mechanics applies to the real universe, as experiments prove, does not only involve unitary transformations. Measurements happen, collapse of the wave functions take place, classical outcomes occur. And this is the standard interpretation of quantum mechanics, and I know there are people here who disagree with this, but nevertheless, whatever theory you have about that, you've got to produce this as the effective theory which applies in the universe as we experience it, as we test it in laboratories. So claiming there's only a unitary Wheeler de Witt equation evolution is simply not correct. It's taking into account only part of the dynamics occurring in quantum physics, as Roger Penrose has emphasized. Wave function collapse, in my opinion, allows time to pass. If you have a time-independent theory which results in an effective wave function collapse, as found experimentally, including derivation of the Born rule, that's fine, because then there is an experienced flow of time at the macro level, whatever its basis. And so I'm not a quantum physicist, I'm coming from the outsides, but as an outsider looking at quantum physics, I agree with Penrose. If you say the only thing that's happening is a unitary evolution expressed in the Wheeler de Witt equation, you're omitting half of the dynamics of quantum physics, and you're omitting the half of the dynamics which related to experiment. You don't get any experimental testing of quantum physics unless you have a collapse of the wave function, classical outcomes, which result in specific, unique meter pointings at a particular time and a particular place. Okay, a philosophical argument is that the past, present, and future are exclusive categories, so a single event can't have the character of belonging to all three. The counter to that is as follows. Suppose E happens at time TE. At time T1 less than TE, E is in the future. At time T1 equals TE, E is in the present. At time T1 greater than TE, E is in the past. Its category changes. That's the essence of the flow of time. So this is a semantic problem, not a logical one. One needs adequate semantic usage and philosophical categories to allow a description of this change, and language usage can't prevent the flow of time. Now, time does not flow. This is incoherent. Paul Davies emphasizes to me. That's correct. And Tim Maudlin emphasizes it well. Time does not flow, it passes. That's a crucial distinction. It is the passage of time that allows rivers to flow. And so I've been persuaded that I was wrong to previously use the word time flows. I should have used the word time passes. And then this philosophical problem is okay, and my reference is Tim Maudlin. It can't pass at the rate of 1 second per second because that's not a rate, it's a dimensionless number. This is false. Just like rates of exchange of money, this is an operator with two slots, each with its own units, and they don't cancel, and Tim Maudlin discusses that in depth in his book. And finally, we've already heard Davies and Ravelli claim time does not flow because it's not needed to describe the relation between relevant variables, which are all that matter physically. Thus, you can always get correlations between position pt and momentum qt for a system by eliminating the time variable. You solve for t as a function of q, substitute it in, and you get p as a function of q. Time has vanished. So time may exist, but it doesn't flow. Only correlations matter. Our response is, yes, you can do that, but the latter model leaves out part of what is happening. That does not mean it does not happen. It just means that you've chosen a partial model of reality, which includes some aspects and omits others. It's a projection from space-time to a phase portrait. That's fine to do that, but it leaves out the way that the continually changing correlations flow smoothly one after another in a continuous ongoing way. So I think that you're saying that a partial model of reality is the whole thing. It's not a partial model. It only represents part of what's going on. Just as an example, Kepler's three laws. The orbit of every planet is an ellipse with the sun at one of the two foci. A line joining a planet and the sun sweeps out equal areas during equal intervals of time. The square of the orbital period of the planet is directly proportional to the cube of the semi-major axis. The second and the third both involve the flow of time. If you're only going to have a relation between dynamic variables and not time, then those two Kepler laws vanish. There's only one Kepler law, and you're missing 2/3 of his discoveries. Yes, of course you measure time relative to clocks. Their ticking measures the passage of time, and without the passage of time, they don't tick. Okay, the error of time and chronology protection. How can a difference emerge between the future and the past on the basis of time-symmetric microphysics? Now, yes, of course, there's a weak interaction-time asymmetry, but there's no way that that weak interaction-time asymmetry is responsible for the biological flow of time. That's not plausible. How does time know which way to flow, and why does it flow the same way everywhere? The second's crucial. If you have any theory for how time flows, which you're going to derive out of the underlying microphysics, you've got to explain why time is flowing everywhere the same way. We don't see time flowing in opposite direction in time when we look out in the universe in different directions. Now, there's no basis for a determination of the direction of time in microphysics alone. The H-theorem, whether it's a Boltzmann H-theorem or a quantum field theory H-theorem, applies equally in both direction of times. Take your H-theorem proof, and you find you've got chosen a direction of time, and you find you do a little manipulation, quantum field theory or statistical, as Boltzmann did, and you find entropy increases with time. Hooray, we've solved the problem of time. But now, let t prime go to minus t. Do exactly the same manipulation, you get exactly the same calculation, and you prove that entropy increases in the opposite direction of time. And you cannot derive the direction of flow the direction of time out of macrophysics because the macrophysics doesn't know anything about the direction of time. So in the standard picture, these time directions are symmetric and you don't get a way of making a choice. In the evolving block universe, the arrow of time arises fundamentally because the future does not yet exist, which is a global asymmetry in the physics context. So for instance, the Feynman propagator can only be integrated over the past because the future space-time domain is yet to be determined. You can only integrate the propagator over something which is already a determined state. So one can be influenced at the present time from many causes lying in our past because they've already taken place and their influence can therefore be felt at the present time. One cannot be physically influenced by causes coming from the future for they've yet to come into being. This is the rationale for saying the past exists but the future does not. If something can influence you, you have to say it exists. So the evolving block universe, the past exists and is developing to the future which does not yet exist. And that asymmetry leads to the arrow of time. And so that's where the arrow of time comes from. The past affects today. The elements in this room were determined in stars in our past. The particles coming in have come to us from the past. The radiation has come from the past. So the past has to exist because all of these events are coming to us from the past. The future can't affect today because it's not yet definite what it will be. And so the possibilities exist, not the outcome. So you can't get an influence coming from the future. Now, an outcome of this is that a long-standing problem is that closed time-like lines can occur in exact solution of the Einstein field equations with reasonable matter content, as Kurt Gödel famously showed. And this opens up the possibility of many paradoxes, such as killing your own grandparents before you were born and so creating causally untenable situations. It's been hypothesized that a chronology protection condition would prevent this happening. But that's an add-on to the Einstein equations. The Einstein equations do not imply chronology protection. It's a selection condition added as an extra add-on for acceptable solutions. And various arguments have been given in its support. But it remains an ad hoc condition added on as an extra requirement on solutions of the Einstein equations, which do not by themselves give the needed protection. The evolving block universe automatically provides protection against chronology violation because creating closed time-like lines requires the undetermined part of the space-time intruding on regions that have already been fixed. You see, you've got a region that's been fixed. To get a closed time-like line, a new part has to come and intrude on a part which has already been determined. Now, what that would require is the fundamental worldlines would have to intersect at that point, but precisely because they're eigenvectors of the Ricci tensor, that means the Ricci tensor, the density will diverge and there's a space-time singularity. And so you're protected from chronology violations by space-time singularities, preventing them from ever happening.
Got around 10 minutes.
Sorry?
Around 10 minutes.
10 minutes, okay, good. Hence, the evolving block universe as above automatically provides chronology protection. We get only space-time with a global time orientation and the Cauchy development of the initial data surface. Okay, I've just got time to talk about taking quantum theory seriously, which has three parts. Firstly, as I've already said, unitary evolution is not all that happens. Real quantum mechanics is non-unitary and irreversible when wave function projection takes place. And to me, this is the core of the flow of time. Flow of time comes from the micro level when quantum indeterminacy changed to classical determinism. Reaching back into the past, there are many hints that the future can influence the past in quantum theory, and we can represent this by a crystallizing block universe. And finally, I'll make a comment on the Einstein Podolsky-Rosen equation and causality. So, in my opinion, and I'm just following the standard outline of quantum physics, I know there are other opinions, but I'm following the standard, the party line. Unitary evolution is not all that happens. Real quantum mechanics is experienced as non-unitary and irreversible when measurement takes place. Wave function projection happens and a classical outcome emerges from the quantum pre-state. This is the core of the flow of time. The indefinite future becomes a definite past as wave function collapse takes place. Now, I must emphasize it happens all the time everywhere. This is not tied into experimental situations. It happened in the very early universe when nuclear synthesis took place. Definite proportions of helium and deuterium emerged out of the hydrogen. They didn't remain quantum superpositions. It happens every time a photon hits a leaf. The leaf, a particular molecule in the leaf receives energy. That's a classical event which takes place. This is happening all the time everywhere. In the very early universe, at the last scattering surfaces, particular interactions took place as the matter and radiation decoupled. It does not relate to an experiment. If a measurement of an observable A takes place at time t star, initially the wave function is a linear combination of eigenfunctions of an operator, and so the wave function is that combination. One, immediately after the measurement, the wave function is an eigenfunction because there's now a definite outcome. And if you immediately repeat the measurement, you'll get the same result. The data for t less than t star do not determine the index n, they just determine a probability for the choice n. And one can think of this as the probabilistic time irreversible collapse of the wave function. The initial state does not uniquely determine the final state, and this is not due to lack of data, it's due to the foundational nature of quantum interactions as determined to the present day. Or at least it's indubitably the way that quantum mechanics is determined to happen in experiments in the laboratories. So if you have a theory where this isn't the foundational way, it's got to work out this way in a laboratory, including the Born rule. So my hypothesis, so you can predict the statistics of what's likely to happen, but not the unique actual physical outcome, which unfolds in an unpredictable way as time progresses. You can only find out what this outcome is after it has happened. So the hypothesis is that this is where the flow of time takes place. The uncertainty of the future changes to the certainty of the past as wave function projection takes place. This happens all the time, everywhere. And I emphasize you can't retrodict to the past at the quantum level either, because once the wave function has collapsed to an eigenstate, you can't tell from the final state which it was before the measurement. Knowledge of the later state does not suffice to determine the initial state, and there's a crucial time asymmetry in the quantum collapse of the wave function, which people don't seem to often talk about. The sets of quantities psi n before are not determined by the single number a n afterwards, and so real quantum mechanics is not time reversible. How does it relate to the earlier part, the evolving block universe idea? Why should collapse of the wave function relate to the average motion of matter in the universe? And my answer to that is wave function collapse is a contextually dependent effect. And I don't have time to talk about this. We could talk about it. But wave function collapse, it depends on the local physical environment, such as the measurement apparatus or a physical system that causes collapse of the wave function, such as a screen or a leaf, and so on. Now, reaching back into the past, there are many hints that the future can influence the past in quantum theory. It goes back to Wheeler and Feynman, which their advanced and retarded potentials, or the work of Aharonov at the present time, his two-time formalism, weak measurements, Kramer's translational quantum dynamics, but crucially Wheeler's delayed choice experiments. There's been an experimental verification of the delayed choice thing, that there can be a distance slit over there, and you measure it over here, and you choose whether the particle would behave as a wave or a particle after it has passed through the slit. Okay, there are many such experiments, and what I want to say is one can incorporate that idea in what I call the crystallizing block universe, where bits of the present are crystallized out after the other ones, and so these surfaces of transition on a micro scale are not as simple as one would have thought. There are little packets which are waiting to crystallize out, representing these delayed choices. And finally, EPR and causality. The problem with the EPR experiment, when you have spin over there and over there, they've been emitted and they're correlated, and you do a measurement there and it instantaneously changes what happens over there. The problem there is instantaneity is not well defined, and it's action at a distance without a physical cause. And so the standard picture, the particles get emitted left and right, you measure over there, and it instantaneously changes over there. I think in the context I've given, a much better understanding is it goes like that, and you make the measurement there, and it travels down and then back up, so it travels down and up. And I think that's the way that one should talk about the EPR thing, instead of talking about things happening simultaneously. And so, in my view, time does indeed pass. In agreement with Tim Maudlin, it happens both the micro, quantum, and the macro classical level. At the micro level, it need not happen simultaneously. It's determined by the macro space-time parts of quantum uncertainty may lag and only crystallize out after the majority of events have become determinate. The classical time-reversible Hamiltonian dynamics are not the norm. Rather, they are sometimes a good approximation to what actually happens in the real universe in restricted physical circumstances. But they do not fully represent the fundamental nature of what's going on at macro scales or even at micro scales. Common sense is right. Time is not an illusion, despite what many physicists may say. General relativity proper time, determined along preferred time like worldlines, is the key. Now, to be done to find out under what conditions transition surfaces can become null and then time-like. I've said they need not remain space-like, but only huge gravitational fields will make them time-like, and it's an interesting thing to work out that, which I haven't done. To work out the ADM equations when that happens, when the 3 metric is no longer space-like, and the relation to quantum gravity. In my opinion, any quantum gravity theory must produce an EBU at the macro level. To me, that's a criterion of a good theory, and the spin foam model does this. For some reason, time's going down rather than up. But apart from that, this is an example of a quantum gravity theory where time does elapse. So that's my view. There is indeed a passage of time, the past and fixed that cannot be changed, as Omar Khayyam wrote so nicely in that beautiful poem.
Two questions. Yeah, can I go back to before I started struggling, which was unfortunately very early on, which was your example of the rocket that had 2 rockets attached to it.
Yeah.
One question I had was, what was gained by adding the story about the rock and the 2 rockets to the basic story of the indeterminacy of atomic decay? What extra work was...
Oh, it curves space-time.
Yes, but isn't the basic issue that you want to address the indeterminacy of the future that you already get in some sense through the indeterminacy of the atomic decay?
Well, as I said, this goes back to the Bohr-Einstein debate, but the crucial point I wanted to make, it's not just the contents of the space-time that isn't determined, it's the space-time itself. And that's what this gives you, because if these objects are massive enough, they're curving with space-time, and so the space-time structure isn't determined until it's already happened.
But you could have exactly that diagram here, simply on the basis of saying, well, at one point there are 2 possibilities, or numerous possibilities. The atom decays within the next 10 seconds, or between 10 seconds and 20 seconds. That's all that's needed, really, to give you that diagram.
Well, it's all that's needed to give you that for the content of the space-time, but for me it's crucially important that the space-time structure as well is undetermined, and that's why I need these to be massive rockets that curve the space-time.
Jeremy.
Well, there's so much each of us has to discuss, so let me just say one main thing which I think will come up often, which happens to be about this picture too. I just would say that a lot of philosophers who are as happy with, as you are, with indeterminism, still like to keep a simple view that the future, there is an actual future or a real future. So they would wish to say about such a tree diagram, you're going to draw a tree because it's indeterminism, that, and this is putting it in rather logico-semantic terms, but it is clarified, is that through each point there is to be what is sometimes called a thin red line, which represents, of course, to the past of that point, there's only one such path, it's the uniquely determined path, but forward of that point there's also a thin red line, which represents the actual future of that point. Now, you immediately realize that, hang on, these lines are going to be everywhere, because every point has just been asserted by Butterfield to have a thin red line through it. But it's not true that every branch going up from a point is coloured red with respect to that point. So I just want to announce that there are ways of having indeterminism with an actual future, and they are coherent.
Okay.
Yeah. So, and that's what I would like myself.
Did you have time for it? David, did you have a question? Oh, okay.
Sorry.
We'll do both if they're quick.
So,
You get that.
Okay.
well, I get this. Sorry. So that's the point. This is not questioning your conclusions, it's not your argument. Somehow, the core of what you're saying, that there's quantum mechanics, and quantum mechanics given is the future, and that makes it strong. I'm not sure I understand this argument. Either the argument is, I do believe that the past is different from the future, because I think the past has happened as an input, and then the asymmetry past and future, it's opposite of the input. Or you don't put this as an input. if you don't put this as an input, the classical story you gave us is given the state of the present, classical. I can uniquely know the future and the past. And the quantum, yeah, I agree. The quantum story you gave us is that I cannot, from the state now today, figure out the future, but the past I know it has already happened. Well, then you're using presupposition about the past. In quantum mechanics, you said so, from a much later comparison. From the state of the present, you cannot determine the future
state in the past.
nor the past. Neither as well. So quantum mechanics equally time symmetry in the future and the past. In other words, from the knowledge of what is the state of the atoms today, you have then determinism, you want to know what will happen, and you have the same determinism of what did happen.
But that's a very interesting point. From the quantum state after a measurement, you don't know what the quantum state was before the measurement, but you have got now a classical outcome which is now fixed and which will remain fixed for the future.
If you believe that classical things exist, but...
if you believe classical states exist, yes. You don't believe classical states exist?
Well, with this, I just wanted to question the argument. It seemed to me that the argument you're laying is liberally. I believe the classical. You're saying if you believe the past classical state exists. So if you assume the past classical state exists, but past or future classical state don't exist, and I think you are not arriving at quantum mechanics, you're just assuming that the past exists.
I'll have to think about this.
I was a touch puzzled by the thought that there's something about the illusion of passage or the appearance of passage which is inconsistent with neuroscience. Now I take it that at any given time there are encoded in our brains records of how things were. Those records are quite interesting because they're records not just of how things were, but they're also records of records which included records which included records which included records in a kind of strange Russian dollars kind of way. And so it's true, it's part of my phenomenology that I can recall a couple of moments ago, and I can recall a couple of moments ago being in the process of recalling a couple of moments ago, and if I try really hard to stretch my brain, I can go maybe 3 levels more up before I can't do it anymore.
Yeah.
But is there anything else on top of that that is somehow a phenomenology as of passage that needs to be accounted for? Now, one answer sometimes people give, and maybe you're about to give it, is yes, there is, because aha, now it's a couple of seconds since you've spoken. I just experienced some more passage. And I say, well, wait on. That just means that the Georgia now has got some records of how things were a couple of moments ago, which included some records of how things were a couple of moments ago, and so forth. And no amount of shouting, now I've experienced a change, points to anything other than we know exists at every time that you exist, which is records of how things were, which contain nested records of other records.
I now have a record in my brain of this little chalk of yours, which I didn't have a minute ago.
Well, did it help you? This guy has a record that wasn't in that other record, that's at that other location, but none of that tells me there's a phenomenology as a passage that needs to be accounted for. Unless, you're theoretically committed to it, and somehow you read that into phenomenology, which seems to me just doesn't. It's exhausted by just records and records and records.
There's more records now than there were a minute ago.
Yeah.
And there'll be more.
Some locations of time, there are more locations of time. The block universe person says you should expect that. Block universe guy says, look, there are all these heads, if you like. The heads up that end have got more records than the heads up that end. That's accounted for by the usual story. But that doesn't tell you there's anything mysterious about the experience that those heads had, which requires you to believe in the evolving block universe rather than the block universe.
Stretch this into the close. We will have more time for close at 5:30 for extending discussions that you need to get fully discussed. So it's